Good morning, everyone. My name is Anit Ranadive, and I'm here from VMware, and I work in the virtual devices team. And today I'm here to talk about some of the challenges and experiences we had while developing our Paravirtual RDMA device. So here's the overall agenda that I'm just going to talk about today. We did a presentation last year regarding our architecture of a device. So I won't go a lot of detail into the device itself, but I'll just give a brief overview. I'll talk about more of the device development process that we had and some of the insights that we had while actually developing the device, as well as what are the challenges that we faced while upstreaming the driver, as well as what are the different aspects of driver development that we had internally. Finally, I'll talk about some of the Passthrough RDMA work that's been going on in a different division at VMware, and what are their experiences and what are their sort of performances that they've got with respect to running a lot of HPC level workloads in virtual machines. And finally, I'll talk about some of the upcoming changes that we want to do for PVRDMA devices as well. So from a virtual machine perspective, the PVRDMA device is really we couple the device with a virtual Ethernet device, which is a VMX-centric device, and an RDMA device as well. So the RDMA device essentially plugs into the OFED stack using our driver and user library. So any RDMA-based applications can take advantage of that of the device without any modification itself. And so any sort of API, or the verbs API that's basically constant between the kernel and the user level, we can actually, those calls pass down all the way from the application to our driver and finally to our backend, which resides within the ESX hypervisor. So the ESX hypervisor has its own native RDMA stack, which allows it to interact with different HCA devices, and in a way that and also helps our PVRDMA backend to ensure that we can service all the virtual machines using a single HCA. And in this sense, we can actually share the single HCA with different virtual machines without actually having SRIV support or anything like that in the physical HCA. And of course, the main sort of motivation for doing a paravirtual device is to be able to support VM migration, or vMotion that we call it internally, and so that you can vMotion a VM across to a different host and actually let your RDMA application continue to run or resume at that point. Next, I want to sort of go down into more details about how we enable, say, zero copy for these applications so that you can actually leverage the RDMA benefits for these different applications. From an application perspective, we also expose with different virtual resources, for example, your completion queues, your queue pairs, and protection domains. And all of those are, every virtual machine has its own set of these virtual resources. So whenever a actual VM wants to create a completion queue or a queue pair, we end up sending these calls back down, all the way back down to the ESX hypervisor, and finally back down to the HCA to allow it to create that particular resource. And we handle memory regions differently than than these resources itself. For memory regions, what we do is that we translate the addresses that the application wants to register. We translate them down to the actual host physical addresses. And those translations are stored in the HCA's IMMU or in the system's IMMU to ensure that the HCA can read or write to that particular address as required. And since we expose these virtualized resources like queue pairs to the virtual machines, the application is able to enqueue any work request that it has. So the work request describe what is the RDMA operation that it wants to do, and the different, what is the size of the operation that it wants to do. And so once it's enqueued that request in the virtual queue pair, we actually can take that same work request, translate it to a different, translate it to the actual physical address that it wants to actually access, as well as actually enqueue that new work request into the physical queue pair that's present on the HCA. And so we can use the internal ESX RDMA stack that's present, and we can perform the same operation as posting the work request down to the HCA. And so once the HCA actually gets these work requests, it can go ahead and actually process them, and it can read the physical queue pair, remove the work request, and say that, well, the memory mapping is already present in its IMMU, so it can go ahead and perform the operation, whether it's reading from the application's memory or writing to another sort of application's memory for doing a remote operation. So in that sense, the operation is completely doesn't involve any of software. It doesn't involve the hypervisor, and the HC can directly access that memory, and in a way, it can actually enable zero copy even for paravirtual VMs. So that's sort of a small overview of what our PVRDMA device can do. Here's the current status of where things are from a VMware perspective as well as from an open source perspective. Our PVRDMA device was released as a software update to ESX 6.5, which is which is an industry standard hypervisor, and it also released with the vCenter management suite and virtualized network management as well, which is all needed to actually run the PVRDMA device for virtual machines. So currently, the device that we've released supports Rocky V1, and it supports RC, both reliable connected and unreliable datagram queue pairs. From memory regions, it supports both. It has support user MRs, as well as in the kernel, it supports DMA MRs and fast register work requests. From the open source perspective, we've recently been added to the 4.10 kernel for our kernel driver, and we've also been and our drivers also is part of the OFED 4.1 RC1 release, as it's a tech preview currently, but hopefully at some point it'll get more included by default or as some other specific option for OFED as well. The user level library also is also present in the RDMA-core 13 release that came out recently, as well as in OFED 4.1 RC1 as well. So next, I'm sort of going to talk about sort of the experience that we had and what are our sort of design decisions that went into how a device should be structured, what are the support, what the device should really support. And part of it comes from the fact that, RDMA APIs have been, there've been a lot of RDMA APIs. So you wanted to ensure that we run those APIs correctly, as well as you wanted to make sure that some of the internal decisions that we did inside VMware, we wanted to make sure that the virtual machines are supported really well. So at least from a VMware perspective, VM compatibility, or the fact that you can use VMs as really a black box to migrate them to different hosts, you can move them to a different host, and essentially let your application resume correctly. And that's something that we always wanted to maintain at VMware, and that's been sort of an internal DNA to use as well. So virtual devices we really want virtual devices to function in the sense that you can, even if a virtual machine moves to a different host that doesn't have an HCA, you want your application to function. Your application at that point shouldn't really break. And from a customer perspective, that's something that we really wanted to enforce internally at VMware. So the advantage is that your customers can leverage different virtualization features like vMotion and snapshots. So even if your VM is, you create a checkpoint of the VM, you can resume the VM later on, and hopefully your application will, can continue to resume as well, and given certain, at certain time lengths. So with those sort of design ideas in mind, we ended up creating these 3 different sub-devices or different transports that we had internally. So we had a fact that if you have virtual machines on the same host, you can leverage a memory copy, which allows you to access to a higher amount of bandwidth, say of the memory bandwidth itself. But in the fact that if one of your RDMA or one of your VMs doesn't have an access to an HCA, you might be stuck around with the fact that, well, now your application won't actually connect to another host or can't actually connect to another VM. And so that sort of breaks gives a bad experience to the customer in the end. So we also have this emulation mode, which uses actually TCP in the backend, so that your RDMA applications can continue to resume over TCP if, for example, you didn't have an access to an HCA. And in certain sense, it might help developers as well So you can build an RDMA application, even without access to an HCA, and you can build it on your dev box or a dev environment. And then once you've checked, then you can sort of move that application into your actual platform or your final production environment to see where it actually has an HCA. And that RDMA application should continue to run, and you'll basically get better performance at that point. And the final transport that obviously is if you have an HCA, you can actually use the leverage that HCA to give you better performance for the RDMA application itself that's running in the VM. So having these three transports also we wanted to enforce the fact that what is the different behavior that you expect from all of these. You want to actually enforce consistent RDMA behavior for all of these transports. You want to make sure that if there are different queue pairs that are from a same VM that are going over different transports, the fact that the behavior is basically seen as the same for all these queue pairs. So if you have a queue pair from one VM talking to another VM, say through the HCA transport, and you have another queue pair from the same VM, but that could be talking to a different VM, say on the TCP transport. So you want to make sure that to the driver itself, all of that is completely hidden. So the driver essentially treats the device as a black box and doesn't really know what's going on in the device itself, except for the fact that it just sees these different queue pairs in different memory regions. They're acting very similar. Unfortunately, the problem with this is that the number of scenarios or testing scenarios that you have actually do multiply a lot. And there are certain corner cases that we've run into where it doesn't necessarily behave well in the HCA, but it behaves well in the TCP case. But since it's around transport, we can figure out what to do. But in the HCA case, since now you have a physical HCA, the errors that you get back from the HCA are sometimes different or not expected. And so that's something that we've sort of wanted to handle in our RDMA behavior as well. So now sort of putting forward these, we have these three devices, and we want to make sure that when you started developing the PVRDMA device itself, we only started looking at the VM to VM or our mem copy, as well as the TCP emulation itself. Because when we started developing the device, we didn't have support for RDMA HCAs in ESXi at that point. And the physical HCA support was actually added later on. So we sort of wanted to make sure that the behavior obviously was consistent. But once the RDMA support was added, we wanted to make sure that VRDMA was really a special ULP to the existing RDMA stack. And we had to make some modifications even to the ESX RDMA stack to ensure that we can support user MRs and other RDMA features as well. So sort of talking about, we have three devices really, but we wanted to ensure that what really is meant by consistent RDMA behavior. We weren't really sure because we've had some experiences with, it works well, or it's mentioned in the IB spec that it's, for example, like the send queue drain state that was mentioned before. It's mentioned in the RDMA IB spec, but it's sort of missing from what existing RDMA NICs actually do. And while the SQD state would actually have been useful for PVRDMA, it's unfortunate that we had to actually figure out another way of being able to support vMotion, and I'll talk about it a little bit later on that. Also, the other question is, how do you define what do you mean by OFED compliance? How do you define OFED compliance really for an RDMA device? There are performance tests and there is QPerf that exists out there as open source. We weren't really sure about was that the only set of tests that we had to pass to ensure that this is what it means to be an RDMA provider, and this is what it means to say that now it's compliant with OFED, for example. While all of those tests run correctly, I don't know if there's another set of tests that require, for example, this test how your HC actually handles error conditions, for example. So if your queue pairs fail, or if you've passed down random API parameters, you want to make sure that your HCA doesn't crash or there's no driver crash. In our case, it's a bit more complicated because we don't want a VM to send down random API parameters and actually end up crashing the entire host. And so that means it'll take down all the VMs in the entire host. So we want to make sure that, what are the different negative tests, from a negative testing perspective, what are the different aspects that we need to care about. And since virtualization adds a bit of more overhead for memory, for managing the VM itself, we wanted to ensure that we get it right, and we don't actually end up, letting one VM crash. Even if a VM crashes, that's sort of bad from a customer perspective. So we wanted to make sure that all our test cases really match, and we want to ensure that we can handle all of those test cases in all the different transports that we have. Next, I sort of wanted to get into some of the specific challenges that we had from, for example, for memory regions itself. Initially, since we didn't have physical HCA support, we were emulating user MRs, or we were just actually making sure that we map the user MRs correctly in the backend to actually do the memory copying, or to ensure that we can write out from the guest memory out to the wire if you're using TCP emulation. When we actually added the physical HCA support, we wanted to ensure that we actually can emulate the user MRs correctly. And the only MR type that was present in OFED before was the physical MRs, which gives you a particular set of mappings of a particular set of pages mapping for that particular R key. And I believe that phys-MRs were actually removed from the OFED a while back, but we sort of had to resurrect it back for our RDMA stack with an ESXi to ensure that we can emulate user MRs correctly in this case. Unfortunately, for DMA MRs, we don't have RDMA read-write support. The reason for that being it's just harder to know what translations you need ahead of time, given that there's no DMA mappings that are passed down from the guest to the hypervisor in that sense. So the only time you would know that an application wants to do or perform a RDMA read and write is when it actually does a post send on the work request. And to actually do it, to do the mapping at that point is essentially a bit late in the work request, and you actually would add a lot more latency for actually processing the work request, because you would have to figure out from the peer, or actually tell the peer that it has to map certain memory into the IOMMU, and then actually do the work request itself. The next aspect is in sort of unreliable datagrams, especially for receives. It's sort of harder to figure out where you want to process the receive. We wanted to synchronize, given that we had 3 different transports, we wanted to synchronize the fact that if you get a UD receive completes in the physical HCA, you have to be able to make sure that you also clear out from the virtual queue pair, or you want to make sure that you also tell the guest that it's completed correctly. In the other case where if a work request completed in the TCP emulation code, there's no way to tell the HCA that now that the work request is completed, well, remove this work request now from the queue. So there's really no way to unqueue a work request posted to the physical HCA. And it would be nice to have an API like that, but unfortunately we are not there today. So our workaround was sort of to have these bounce buffers posted to the HCA, which means that we would enqueue a certain set of buffers which are completely mapped to a different memory than guest memory, and you let the HCA actually complete your UD work request in those buffers itself. And so once we get a completion where that these buffers have been, that work request has been completed, we would actually copy out from the bounce buffers back into the actual guest memory for to complete the actual guest work request. And so this sort of shadow copying is actually simpler for UD, because UDs are confined to your maximum MTU size, which actually limits the amount of bounce buffers also we can post. So it's sort of a way around that, to work around the entire UD receives, but that's something that we had to anyway do, unfortunately. vMotion support. So I think vMotion has been, we're really glad to have vMotion support for our PVRDMA device. Unfortunately, at this point, it's still partially supported in the sense that we can't actually talk to native hosts. We can't allow PVRDMA VMs to talk to native hosts because of the way we expose virtualized resources. Hopefully, moving forward, we want to really expose physical resource identifiers to the guests. that would enable it to actually allow it to talk to native host, because application might exchange RDMA information out of band, and we want to make sure that it's all synchronized and the HCs can actually talk to each other based on those identifiers. And to do that, we would need support from the hardware itself to ensure that if you vMotion a VM to a different host, you could actually recreate the same queue pair numbers, or recreate QPs with the same queue pair numbers, or recreate MRs with the same remote keys as well. So that will allow your communication to resume when your native host and your VMs can really then resume your queue pair connection. And obviously, the fact that currently we are limited by the point that we can only stop communication once we've completed a work request. We can't arbitrarily stop communication in the middle of a work request, because we don't have enough information from the device or from the HCA regarding what is the state of the work request when you stop, when you say, for example, when you reset the queue pair, for instance. So we would need more additional APIs even from the HCA to say that, well, now this queue pair is suspended, so you have this notion of suspend state, and you can identify what is the state of the work request, at what point how many bytes were transferred. And then when you resume a VM on a different host, you would actually have more information, or you can let the queue pair actually resume the connection itself from that point of work request. So even the state of your memory region is the same before and after vMotion. Finally, coming to the transport or the emulation itself, or the Rocky support, we actually were stuck at Rocky V1, and we're still stuck at Rocky V1 because when we started developing the device, there was no Rocky V2 support natively in different distributions, and we didn't have a good idea about how Rocky V2 would really pick up. And to be honest, we didn't have even Rocky V2 support in our ESX hypervisor. So there was just not enough time for us to ensure Rocky V2 support, or we weren't confident enough that we could do Rocky V2 support across all our transports. So we just said, well, let's go with Rocky V1 for now. Finally, for us, it's much harder to do updates to a device just because we are tied to the actual hypervisor software updates as well. And the way we ensure VM compatibility is through virtual hardware versions. And we want to make sure that if we update a virtual hardware version, we want to make sure that's compatible with a few prior releases as well. And so it's much harder for us to do. We can't update the device just with regular firmware updates, but we also have to tie it to our virtual hardware version to ensure that it's a much better experience even from a customer that's deploying ESXi, for instance. Right. That section was on all the device development challenges that we had. Now to sort of talk more about the upstreaming efforts that we've had and what are the issues that we faced there. Some of it experiences has been really good. The support from the open source and OFED community has been great, and we are really thankful for letting us be accepted into Linux kernel. So when we started developing the driver and the library, we wanted to actually ensure that we didn't want to change a lot of things, so we didn't actually go with the upstreaming code that's present and continuously change what's out there. So we want to stick with the consistent APIs between the user level and the driver layer, and as well as the device. And that was essentially easier for us to then actually do testing, because since the APIs actually remain constant, we can actually ensure that we can test them correctly and test them very more successfully if we change anything in the device itself. So we actually had different repositories for the driver and library, and internally when we added a new API, added a new device functionality, we would just add a new test for testing that device functionality that would be consistent for the different transports we had. And that would continuously run in our automated environment to ensure that nothing really broke and there was no regression of performance itself. Overall, this was actually my first time upstreaming in a driver to the Linux kernel, and it's been a great learning experience. Thanks to all the open source folks that reviewed our code. Finally, when we got to see the applied message from Doug, that was really great to actually awesome to actually see that. But it's also, from an RDMA provider perspective, we end up sort of doing double duty, just not for the fact that there's a driver as well, but you also have the user level library, which you also have to upstream as well. And as I said, it's overall it's been a great learning experience for us, and we would gladly help around with any more OFED support as well. Some of the other changes that, while we were upstreaming, there were another bunch of changes that didn't occur, and which some of us, it caught us off guard because we weren't prepared for it. And maybe just not we were aware of what was going on the Linux RDMA mailing list, but some of them were related to the ABI changes that were there. And there were different other changes with regard to, say, the rdma-core library that was recently added. Also, we have to keep updated with different sort of API changes that went on in even the API changes that went on in the upstream. So in the sense that I think we sort of had to get a handle of things pretty quickly. It probably was it wasn't as good for us because we ended up we wanted to sort of release the driver and upstream code along with the ESX hypervisor release as well. So some of that got delayed. But I think that was just probably our efforts to sort of look at the upstream code more closely and probably work with that in the future. I think we'll probably have more efforts to work with the upstreaming code more closely. Also, we're also looking at OFED 4.8, and the integration process for OFED 4.8 was a little bit different. And so you also want to make sure that we got added to OFED 4.8 so customers could actually use PVRDMA in their environments as well. And finally, from a fixes perspective for the driver, we ensure that we maintain or we know where the driver actually has been cross-ported to using different versions. And the versions actually want to tell us to keep track of the different fixes that went into the driver. And so it tells us that, well, Red Hat got this version of the driver, so we know this particular fixes are present in that driver, etc. So that sort of concludes part 1.5 of the talk. The rest of the talk is just sort of focused on the other efforts that we've been doing in VMware regarding RDMA support. And the Office of CTO is doing some more efforts on Passthrough RDMA, where they actually take the physical device and pass it through to the guest itself. That it sort of avoids the hypervisor and gives you probably the best performance from an HPC in the virtualization perspective. So the effort is by Na Zhang and Josh Simmons. I mean, Josh has presented at the OFA conferences a few times, and they wanted to discuss some more performance-related efforts that they're doing for HPC-related applications. Overall, the technology that they use is called VM Direct Path IO that just allows the entire HCA to be passed through to the guest, and the guest has complete control of the HCA. They have a 32-node Dell cluster, which includes 100 gigabit per second EDR cards. They've been doing some more HPC application performance testing, and initially, one of the first application that they used was a weather simulation app, and as you can see, they've in various setups, they've actually got very close to native performance as well. They've got more than almost 90% as close to native performance. So the other application that we used is the Star CCM Plus, which is a sort of fluid dynamics sort of based simulation application, and they use different kernels that do fluid dynamics as well. Even in this case, they've got most close to, in most cases, they've got more than 90% of native performance. LAMPS is as well, and is a molecular dynamic application as well. I think they're still investigating why, in certain cases, LAMPS actually perform pretty badly. It's almost close to 70% of native. And I think they want to get it as close to native as possible. And so I think they're still looking at tweaks in the hypervisor to figure out what's the best way of trying to allocate memory, or trying to figure out what's the impact on why really the application performance is dropping for certain request sizes. And finally, they also looked at NAMD, another molecular dynamics code, to ensure that you get almost close to native performance, and your hypervisor is not doing, is not doing bad things at this point. All right, to finally conclude the talk, our driver and libraries have been accepted upstream, and we are really grateful for the open source efforts and the OFED community in general for helping us in our work. From a Paravirtual RDMA driver RDMA device perspective, there are some unique challenges to ensure that we get everything right, and we want to ensure that in the end, the customers using your RDMA device actually have the best experience. Overall, it's been a great experience working with the open source community. Moving forward, we wanted to look at Rocky V2 and shared receive queue support. So there'll be more patches forthcoming for the PVRDMA device. Hopefully, we can contribute even to other open source efforts, or open source RDMA related efforts, and that's something that's been on our radar. In general, RDMA has been, since we're all here, RDMA is becoming more even interesting in virtualization settings, and it's just gaining a lot more importance for other enterprise level applications as well. Passthrough RDMA has improved significantly in terms of performance, and that's because of hardware-related changes and as well as different supports from we added more improvements to our hypervisor as well. So that's all I had today. Thank you for attending, and thank you for giving this opportunity to present. And I can take any questions if you have.
I just wanted to ask about for your PVRDMA, what the performance is, especially, there's some cases where you're using virtual queues and bounds buffers and so forth. So how's your performance?
So I think we presented last year regarding performance itself. We were getting close to around 5 microseconds for standard operations. And I think for write operations, a little bit lower. I think maybe around 3.54 microseconds. It hasn't really changed much, and since I didn't want to present, the same numbers again. But that's sort of the ballpark figure that we've had.
Okay, so that's a latency figure, and then do you end up consuming a lot of CPU for those bounce buffers to move the data and stuff?
Not necessarily. It's usually a mem copy of 4 kilobytes, whatever, the maximum MTU sizes. So that's probably not much in terms of CPU cycles itself.
Okay, and then when you do a migration, you talked about a consistent RDMA model, so perhaps you don't necessarily. You could imagine a scenario where on the starting place for your migration, you have certain optional capabilities, but you don't have them in the destination.
Right.
So do you just disallow that, or you fall back to the software when you move over there, or what do you do?
So we just fall back to the software at that point. Because even if, say, for example, if you had an HCA with SRQ support on one host, but if you vMotion the VM to a different host that has an HCA but no SRQ support, we would just rely on the software emulation code at that point.
All right, and then when you actually are doing the migration, are you closing connections, or are you trying to maintain live connections throughout? Because then you have queue pair renumbering, you've got, maybe you need to SQD pause them, or there's all kinds of things you can think of which might not work. So from an application perspective, the queue pair is still in the RTS state. That doesn't change. So that's the virtual state that's always maintained for the lifetime of the VM. Only on the hardware side, we actually drop all our queue pair connections. So once we've paused the VM, there's absolutely nothing running in the VM at that point. We actually end up dropping all the physical RC queue pair connections or whatever. And then when we migrate the VM itself to a different host, we will recreate those physical RC queue pair connections. Okay, and then you already talked about the R keys and stuff like that. Even for the UD, though, right? Somebody else has your queue pair number or whatever. You have to re-resolve all those things.
Yeah, so we have to re-resolve. So we have we sort of have a peer-to-peer protocol which figures out all the resolution. So we would pass the translation between, say, the virtual key to the physical key, and the virtual queue pair number to the physical queue pair number. And so even when before a VM actually resumes, we exchange all the new information beforehand. So at the sense that in the vMotion itself, you would resume or sort of resolve those transports correctly, and to ensure that when you actually hit or post the first work request on the virtual queue pair, the queue pairs are actually connected at that point. The physical queue pairs are connected at that point.
All right. Okay, thank you.
Hi, Aditi. Good presentation. I have a couple of questions. One is, in the pass-through case, I assume there's no support for vMotion.
No.
There's no way to store, recover with...
No, not currently.
Okay. Is there a plan?
Well, yeah, that's why I'm here. I mean, hopefully we get hardware support and then we can do that.
Okay. My second question is with MPI support in paravirtualized environment. Did you guys have any analysis on that with real applications, especially the pass-through showed some good applications like LAMP or NAMD. Do you have any such studies with paravirtualization to see its relevance to HPC?
So we've had, so I think, currently I think our PVRDMA support is, we actually have a limited number of queue pairs and a limited number of MRs that we actually create. And some of that limits the size of the application that we actually can run. So we definitely run some smaller scales of MPI-based applications. We've run NAMD and everything. So we had a demo in supercomputing last year, which we talked about running NAMD on PVRDMA as well. And also doing vMotion using for those VMs running NAMD at the same time. So, but it's not at the scale of the pass-through device, pass-through RDMA that I've shown here. It's sort of been two VMs talking to each other at this point, and trying to ensure that the connection actually is successful and the MRs that they create actually work, and all the queue pairs that they actually connect, everything works basically.
Thanks. Sorry for taking up your time. Third question.
Okay.
So do you have any production paravirtualized environment as of today, which you could give an example of that might help? Thanks.
Not yet, at least. I think we are working with different vendors. I think internally at Dell, I think they are looking at some testbed for PVRDMA as well.
So I have a related question to the last there. I'm just curious what your RDMA test environment is like. Are you looking at just InfiniBand or Rocky, iWarp, different hosts, or rather guest OSs?
Yeah, right now, it's just Rocky. On the physical side, it's just Rocky support for now.
So I have a couple of questions. One is on, if I understand correctly, just a clarifying question. So on your PVRDMA driver, you have virtual, basically like virtual queue pairs that somebody posts a virtual or a request to, and then that traps into the hypervisor, and then it translates that work request into a physical work request that's posted on the physical queue. Mm-hmm. And so when you do that, then is the actual DMA is 0 copies still?
Right.
So for large messages, you should get good bandwidth, right?
Yeah.
And then you said there was some additional latency because you do have to do that translation. So
Right.
instead of 1 or 2 microseconds, you're 3 to 5 or something, right?
Yeah.
Okay. And then the second question, or comment, I guess, it was around your comment about the problems that you had in making sure that the semantics of your RDMA devices that are basically software emulated over memory copies or software emulated over TCP, it was difficult to understand what the actual hardware semantics were of each different type of device, so that you could give the user the appearance of
Right.
the exact same semantics. And you had said that there might be a need for some compliance tests for the verbs for semantics, right? I do know that we have the interop program that tests interoperability, but that's at the wire level between two devices, but not at the API level. So and I know that at least in the OFI WIG, and I think there's a talk on this, they're talking about doing something similar for OFI, where there's a set of software compliance tests that test the semantics to make sure each provider is providing a correct semantics.
Right.
Maybe there's an opportunity to do something similar to that for verbs.
Yeah, that would be great to have actually, even for us, for RDM providers. So everybody has a consistent experience for
And then just,
how they behave.
just one quick follow-up question. So I know that the paravirtualized driver has been upstreamed as open source. I assume though that the hypervisor part of it, the backend is closed source, or is that open source as well?
No, that's closed source.
Yeah.
It's through the SX hypervisor.
Just one more question. Because queue pairs could be very they could be thousands of elements long. Do you limit that, or do you limit how many real work requests go into the hardware QPs to prevent any significant delay of starting the vMotion?
No, so I think we have so when we expose the device itself to the RDMA stack inside the guest, we tell it what's the maximum number of work requests it can post at a time. So I think that's much smaller than what the physical limits are.
So usually you wouldn't, you're not in a position where you have to hold off putting things into the physical queue just to be sure that the vMotion can always start quickly.
Right, so the problem is once you've posted the work request to the physical, we can't do anything at that point really, right? So for RC QPs, we sort of say that, well, if the guest posts something on the virtual queue pair, we do post it on the physical queue pair as well.
Right.
If it's not vMotioning already. Or if
I
it's not
see.
in the
So it's
process.
really only for translation. It's not some latency issue where how long you have to wait to drain the queue and stuff like that. Okay. All right.
This is a little more elaborate from the question that the gentleman asked. Is there any initiative to open source the PVRDMA backend or any work going on in KVM community to do that?
No, I don't. That's something that I'll have to talk internally, but not at this point. All right. If there are no questions, thank you very much.